Okay, so first section we'll look at this week is 4.4, and it's on radical functions. So those are both examples of radicals. Basically, we're looking for functions that have a root in them. Okay, could be a square root, could be a cube root, could be any root. So things we're going to do is we're going to graph. So we'll practice a little bit of graphing. We're going to learn that pretty much any odd root has a certain look to it, and then any even roots, like square roots, fourth roots, those have a different look. But once we know what odd and evens look like, sketching is pretty easy. Much, much easier than what we did last week. So any expression that has that notation, where this number is greater than 1, is called a radical expression, or just radical. Right? We're going to be looking at radicals most of the time that are in an equation, right, when we get to solving. Right? So we'll have to, most of the time, factor or use quadratic formula, but as long as you know how to do those two things, that's all that ends up happening with the kind of radical equations I give you. This number right here, the small n, that's called the index. Okay? And the index always has to be an integer. Because you can take a square root, you can take a cube root. There's nothing in between the two. There's no such thing as like a 2.5 root. Right? Square root, cube root. Okay, when we're dealing with radical functions. The thing under the radical, the a, that's called the radicand. It's just the thing that's under the root. And then the actual symbol that looks kind of like a check mark with a horizontal line in it, that's the radical sign. Is there any questions on any of those terms? Kind of a lot of vocabulary up front. Index, radicand, radical, radical sign. Okay, also I didn't take the calculators out because you don't need them. I am going to do some things on the calculator, but it's actually better if you really just watch me, because I don't think we're doing anything new that you haven't done before. Okay, so if you have a root and there's no index, like if you just have this, we assume that the index there is a 2. That's a square root. You can put the 2 in if you want. Most people don't. Unless the number is not a 2, then you have to put it. Now, radical expressions can also be written with fractional exponents. Does anybody know what power you can raise x to? And it's exactly the same as taking a square root.
To the 1/2.
Yes, to the 1/2. So if you want to take the square root of something, and you didn't have a square root button, but you had a power, you can still do it. You can raise it to the 1/2. How about a cube root? Anyone have a guess what fraction that a cube root would be?
1/3.
It would be the 1/3. Yep. How about a fifth root?
1/5.
To the 1/5. And the reason why we might, especially in this one, change that to the 1/5, because then you get this. You have x to the 4th to the 1/5. What's the rule when you have a power raised to another power? Multiply. And what's 4 times 1/5?
4/5.
4/5. So by using that rule of changing it into a fractional exponent, you can actually simplify that down. X to the 4/5. Any questions on how to write radicals as fractional exponents? Okay. So, when we're solving an equation, let's say like this, square root of 9. What is the square root of 9? And?
Plus or minus 3.
Plus or minus 3. There are two answers. When the directions say principal root, like the principal square root, principal cube root, principal basically means like they want one answer. So we're going to separate it into two cases. Right? How to do it if it's odd, how to do it if it's even. So let's say I wanted you to find the cube root of 64. Remember the letter under the root. If I just go back for a second, the letter under the root, that's A. N is the letter that's on the outside, that number right there. So, what's A in this case? 64. So I'm going to write it like this. 64 equals X, I don't know. What's N in this case? 3. So if in Algebra 1, or if I was trying to explain what it means to take a cube root, I would say it means to figure this out. Figure out what number you can raise to the third power and get 64 as the answer. Which in this case, does anybody know what it would be? 4. Yep, 4 times 4 times 4 is 64. Right? So if n is odd, to take a cube root, you're basically trying to figure out what number you can raise to that power to get whatever number they gave you. All right? And there's only one answer. 3. Okay, that's it. There are imaginary answers. Okay, remember, we've mentioned when you take a root, there are as many answers as the root. Cube root 3, 10th root 10. It's just you start getting into imaginaries. So we're just focused on real. Now, if you're doing an even root, first thing I say is this, the number under the root, has to be greater than or equal to 0. Why? What would happen, like if you tried to take the square root of a number that wasn't greater than or equal to 0?
You can't,
Why?
because you can't have the square root of a negative number.
What would happen?
It would get a positive. You get an irrational number. Or an imaginary.
Imaginary, yeah. So first of all, anytime you're dealing with a square root, fourth root, whatever, the thing under the root has to be greater than or equal to 0. And the second part is I want the answer that is non-negative. So if I asked you to find the square root of 16, you're basically solving this equation. X to what power gives you 16? So I'm asking, what number can you square and get 16? And I want the non-negative answer. So what would that be in this case?
4.
4. Yes, negative 4 also works. But I wanted the principal root, which is 4. Okay, any question on that? Also, when we get into graphing, when we do a graph, we are only going to graph the principal root. We don't graph multiple answers to the same problem. When we do graphs of roots, everything has one answer all the time. It's the principal root. So, let's look at this. When you take the square root of a number, what's your first thought? Does it get smaller or larger?
Smaller.
Smaller. Okay, let's try a couple. So on the left, I've got a number. On the right, we'll do the square root.
2.
Square root of 4, it got smaller. Square root of 18, between what and what?
4 and 5.
Yes, somewhere between 4 and 5. What is it exactly?
4.6.
4.24.
Are you right?
Okay, got smaller. How about the square root of 1?
1.
1. Didn't get smaller. Okay, so that's the first one we've done that it didn't get smaller. Let's look at this one. 0.5.
Somewhere between.
So think about, you're going to multiply two numbers together, and you want the answer to be a half.
Wouldn't it be like 0.6 something?
Yeah, it's got to be bigger than 0.5, right? Because if you did a number that was 0.5, if there was 0.5 times 0.5, that's a quarter. That's too small, right? A half times a half is a quarter. No, so it can't be smaller than 0.5. It actually has to be bigger, right? So if you take, let's see what it is. If we take the square root of 0.5, I think we get about 0.7.
Yeah.
0.71. So what happened that time? It got larger. Right? And if we take the square root of 0.2, you're thinking of two numbers you can multiply together and get 0.2. The numbers have to be bigger than 0.2.
0.4.
Probably about 0.4, 0.45. So, anyone think they can generalize when you take a square root? What happens? We can't just always say it gets smaller. We have to be a little more specific. Yeah?
If, like, A is greater than 1, it'll get smaller, and if A is less than 1, it'll get larger.
Yeah. If it's greater than 1 and you take a square root, it gets smaller. Less than 1 and you take a square root, it gets larger. One more case. Exactly 1.
If A equals 1, it equals 1.
Stays the same. Yep. So, we're going to keep that in mind, and we're going to graph some roots. We're going to look for some patterns. Okay, just kind of see what these look like. Is anyone familiar with what any of these already look like? I mean, they all kind of look the same. Because it's a time.
Oh, they doing daylight savings.
I think they're trying to fix it because they.
Hey! It's almost time to go home!
Technically, it's 3 o'clock, so we'd already be home.
Now,
Let's go!
okay, do people know how I just typed in 4th root?
No.
Yeah.
No idea.
So, to type in a root other than like a square root or cube root or anything like that, okay, you have to press 6, and now that's going to be my index. Math, and go to the 5th option down. If you do that, it will automatically change that 6 into the index. Type in the index, and then go to the 5th option under math.
Do it one more time for me.
So, type in the index, math, option 5. And then type in your argument, or your radicand. Argument, radicand, same thing.
So are they going all the way around?
Yeah.
Why did they go backwards exactly?
You talking about this?
Because the clocks don't spin backwards.
No, I don't know. They have to.
Oh, they have to go 23 hours.
Oh, 11. Whoever has that job, probably.
Oh yeah, you're right, 11.
Pump.
It goes up.
So, yeah, we want to see, I'm going to make that bigger, but I want to try to look for some patterns. Okay. Did anybody notice anything about those graphs?
The bigger the index, the less of a slope you're gonna have. Not less of a slope, but more like evened out, like less options. I don't know how to word it.
Maybe. I know what you mean, but that would depend a little bit. I'm going to have to zoom in more to see this better. But for now, I want it to stay zoomed out so we could see it bigger. Yeah?
Well, like when the graph hits 1 on the y-axis, it like starts pulling out more, especially for the 6th root.
Okay.
Yeah, whatever you call that.
Yeah. So it does start the 6th root, the black one. That's the 6th root. It starts to flatten out more. Yeah?
Yeah, I was gonna say like the larger the root gets, it looks like the angle is like sharper or something, I guess.
Oh, okay. Like the way it kind of turns.
Yeah.
Yeah. Let's zoom in a little bit more. I want to zoom in maybe from 0 to 2 and 0 to 2. Okay, just look at that spot. How about in terms of the quadrants that these graphs are in?
It's all
It wouldn't go
Right.
under.
So that tells you about the domain, right? The domain of these is basically from 0 up to what?
infinity.
Infinity. Yep. So we can see that looking at the big picture. Now let's zoom in and look at what's happening here. So there's the blue one, red one, and we're going to see the black one again in a second. Is there anything else you notice about all those graphs?
They're all crossing around.
The
They
one,
all cross at 1, 1. What else?
so they all, well, for like black, it starts out the strongest, but then ends the weakest. And then for red, it starts out in the middle, ends middle. And then for blue, it starts out the weakest, but ends the strongest.
So yeah, the way they are on top, which one is above which, it all changes at 1.
Yeah.
So whether or not you're saying a square root is always on top of everything, well, it depends. After 1 it is. Before 1 it's the opposite. It's under everything. And these all start at the origin. So all the graphs start at the origin. They all go through the point 1, 1. And the domain is 0 to infinity. How about the range here?
0 to infinity.
Yeah, 0 to infinity. And I think that's pretty much everything that's important. Now this is true with all even roots. I just did a square root, fourth root, sixth root. But if I did an eighth root, you'd see more of the same pattern. So the origin and 1, 1 is a point on every graph. Okay? The only way it wouldn't be is if you shift it, which we can. Right? If we shift these graphs up or down, they'll all have a common point, but it wouldn't be 0, 0, and 1, 1 anymore. That point would shift. The domain and range are both 0 to infinity. Okay, both of them. And between 0 and 1, so in this section, between 0 and 1, you can see that a sixth root is the highest. The black one is on top. And the square root is on the bottom. So between 0 and 1, when you're dealing with decimals, the higher the root, the higher the number you get. When you go after 1, it's the opposite. The higher the root, the lower it gets. So if I bring this back up, after 1, a square root is on top of a fourth root. The blue one is on top of the red. The fourth root is greater than the sixth root. So the red one is on top of the black. But the behavior all switches right at 1. And you guys kind of saw that in this table too. I asked you, like, is it getting smaller or larger? And we figured that out. Changes right at 1. Okay. So any questions on
So they'll say indices on top,
indices? Yep, radicals with even indices.
and indices are that essentially the index.
Yep, anything with an even index. All the even indices. Now we're going to take a look at odds. First of all, what if I asked you this, the cube root of 64? What would you get?
4.
4. What if I asked you this, cube root of negative 64?
Imagine. 4i.
Well, so you can't think of a number that you can multiply by itself 3 times and get negative 64?
Oh, negative 4.
Negative 4 times negative 4 times negative 4.
Oh,
Yeah. So when you're dealing with odd indices, it's okay if x goes in the positive or the negative direction. So what do you think that's going to mean about the domain?
The domain's going to be negative infinity to infinity.
Yep. So these graphs go in both directions. Even roots have a start point and go one way. Odd roots don't. They look different. So let's take a look at what an odd root looks like. Let's graph. I mean, you could do a third root and a fifth root, or a fifth root and a seventh root. Just any 2 roots. Can someone remind me, how do I type in a cube root?
You hit 3, math 5.
3, math, 5. Yep. And we'll do a fifth root, 5, math, 5. There is actually a button for cube root. Well, actually, it's not a button, it's a menu option. If you go to math, option 4 is a cube root. But if you have to do anything other than a cube root, you got to use option 5.
Why would you need specifically a cube root button?
Because, I don't know, I guess a lot of calculators have them, so they probably thought they'll add it as a menu item. But yeah, you really don't need it. I think cube roots and square roots are just very common. Square roots are really common. That's why they give a button to it. But cube roots, those are also kind of common. All right, so let's graph these. First thing you should notice right away, it's going in both directions. Okay, so definitely going in both. I think to see what else is happening, where do you think we should zoom in here?
Same way we did before.
Yeah, I would zoom in. Let's go zoom 2. I'm going to do zoom in, and I'm just going to put the cursor right at the origin and hit enter. So this is like negative 2.5 to 2.5, roughly. And I think it actually gets so steep in the middle it looks disconnected, but it's not.
So the
All right, let's make that a little bigger and take a look at it. Okay. Anybody notice anything here kind of along the same lines as what we did before?
Yeah, they intersect at -1, -1, and 1, 1.
Anywhere else?
0.
Yep, 0, 0. So what that basically does is it breaks this into 4 sections. Section 1, section 2, 3, and 4. Section 1 is less than -1. The next section is between 0 and 1, between -1 and 0, between 0 and 1, and then greater than 1. So we got all the points where they cross. What did we say about domain?
Negative infinity to infinity.
How about range?
Same thing.
Same thing, yep. What sections is the graph in blue on top?
2 and 4.
2 and 4. And blue was the cube root. So the cube root, how can we say this? The lower the root, if you're in a section like 2 or 4, it'll be on top of everything. In sections 1 and 3, the lower your root, it's below other things. Okay? So like if I did a 7th root, right? If I did a 7th root and I was in section 4, it would be underneath everything. Or section 2, it would be underneath everything. Now, if I did a 7th root in section 1, it would be on top of everything. Okay? So I think we've got everything that's important. Let's just write them down. So those points are common to all odd graphs. Those 3 points. Domain and range, both negative infinity to infinity. Now, this part it gets a little confusing, which is why I use the section numbers. I think that makes it a little clearer. But if we put this back, because we're premium now, less than -1 is section 1. Between 0 and 1 is section 3. So in sections 1 and 3, the higher the root, the higher it is on top of other graphs. In the section that's between -1 and 0, which is 2, and greater than 1, which is 4, the higher the root, the lower it is. Okay. So it's a little hard to remember, but you really don't need to memorize it, because if you ever don't remember, just graph it on your calculator and look. Look at the 3rd root, look at the 5th root, and look for the pattern. Okay, but odd roots are kind of complicated. They end up crossing each other a bunch of times. And it's basically a mirror image, that graph is symmetrical. If you thought about it, mirror image it, it's the same thing. Okay, so any questions on that?
The clock went too far.
Yeah, it's got to go around 13 times, I think. It's the magic. I don't know. It might just keep doing it for a while.
That sucks.
So, even roots, odd roots. Now, we've looked at transformations with pretty much every function we've studied. What happens when you add or subtract? What kind of transformation is that? A stretch or a shift?
Shift.
It's a shift. What happens when you multiply?
Stretch.
Stretch. What happens when you do it inside the function? Is that your horizontal or your verticals?
Vertical.
No.
Inside is the horizontal.
Oh.
Outside is the vertical. Okay. When I say inside, this is inside the radical function. So let's just go through them. What's that plus a going to do?
What? Horizontal.
Yep. So we're going to call that a horizontal shift. Horizontal shift. What about D?
That's a vertical.
It's plus, so it's still a shift, but this is going to be a vertical. That says vertical shift. Pen's kind of thick, so it's hard to write it. How about B?
Horizontal stretch.
That's a horizontal stretch. Horizontal stretch. And C? Vertical stretch. Now, remember that Everything that you see for horizontal is the opposite. When you see plus on a horizontal, it's going to move it to the left. When you see minus, it's going to move it to the right. Put a big number in for b, like 5. A big number is actually going to make it smaller. Like 5, the square root of 5x would be compressed. C and D do exactly what you would expect. Plus is up, minus is down. Put a big number in for C, the graph stretches out bigger. Put in a small number, like 1/3, compresses smaller. So we've studied these transformations before. Let's just see if we can do it here. So let's look at g of x. How would you graph g of x compared to the square root of x? Like if you had the square root of x, what would you do to it to turn it into g of x? Well, think about that minus 2. What's the minus 2 going to do?
Horizontal stretch. I mean, shift.
Which way?
To the right.
2 to the
Oh,
right,
right.
yes. So, to graph g of x, shift square root of x, right 2 units. That's what they were looking for. How about this one? H of x.
Shift to left 3.
Yeah, I'm just going to write that part. So shift square root of x, left 3 units. How about this one? What? It's not quite what we're looking for. What do you think I should do first?
Which negative x, so it's negative x plus 3.
Yes, write it like this. So it's the square root of negative x plus 3. Now, there's how many things are happening here? 2. What's the first thing you would do? Well, that negative is in the spot where b is. So b comes after doing a.
Oh,
So we got to do a first.
Doesn't x have to be? No, never mind.
Oh, Abby?
What?
Could you tell me what the first thing we would do here is?
I don't know.
Well, what should we be looking at first? There's 2 things to look at. Which one should we focus on first? All right, let's go back one more step. Look at that equation. So we put the letters in alphabetical order as to which one we should focus on first. So if we go back down, what is in spot A?
The right one.
3.
Plus 3. So what would that tell me to do? It's the same thing we just did. Yes?
Horizontal shift 3 units.
Left. The plus 3 is exactly the same as the one we just did up above it. Plus 3, plus 3. So start by shifting left 3. So shift left 3. Now that negative is in the spot where b is. It's a negative 1. So think of it this way. Is there a stretch happening?
No.
Not really, because it's a negative 1. If it was a negative 2, then I would say yes, there's a stretch and the negative is doing something else. But it's a negative 1. So there isn't really a stretch. But what does the negative do?
Makes it imaginary.
What?
would have reflected along the y.
Yeah, it's a horizontal reflection. because anything inside is horizontal. So that's a horizontal reflection.
So if it was like a -2, would it be a horizontal reflection and stretch?
Yep, you'd write both. Horizontal reflection over the y-axis and reflect or stretch by a, let's see, if it was a 2, that would actually compress by a factor of 2.
Huh.
Yeah. So yeah, you'd have both a compression and a reflection. So horizontal reflection. Horizontal reflection means this. If you had this, now you have that. It's mirror imaged over the y-axis. So let's graph that and just take a look at it. Square root of 3 minus x. So second square root, 3 minus x. And I'm going to zoom back out so we can see it bigger. Does that graph make sense with what we have? What do you think?
Yes, it does.
Yes.
Even though it says we went left 3?
Wait.
So it's okay. It makes sense.
It makes sense because we reflected it. If you wanted to think about it like this. First you went left 3. So first you did that. Then you mirror imaged it. So now, when you mirror image it, this point is going to end up here. This point basically stays right where it is. And it goes that way. So yes, even though it kind of looks like you said you shifted it right 3, it's only because of the reflection. Okay. Any other questions on that one? It's not good.
I think it's fine.
So when we make a sketch, what we want to do is figure out where the point that was at 0, 0 went. That I call that point one of 2 things. If it's an even root, I call it the start point. If it's an odd root, I call it the center point. So basically figure out where your start point or your center point went, depending if it's even or odd. So to find that coordinate, we've got to do 2 things. First thing is find the x value. Very easy to find the x value. Take the radicand, set it equal to 0. That's going to be your x value. So when we have a problem, set that equal to 0. That's your x value. Of the start or the center. Depends if it's even or odd. Then, to find your y value, well, you're going to have a formula like this. Y equals, if you know the x value, just use substitution to find the y. Plug x in, do it out, and then get the y. Now, I say use substitution, you really don't even have to. You'll see why in a minute. You're going to be able to tell what the y is just by looking. Now, I said in addition to finding that point, you also want to get some points to the left and to the right of that point. Why did I write if applicable?
Because it won't always have points left.
Right. If it's
Or right if it's in front of you.
yeah, if it's an even root, you're only going to have points going in one direction. So if you try to plot points in the other direction on your calculator, it's going to be imaginary.
Oh god.
So don't go in the wrong direction on an even. On an odd root, you really can't go wrong. You're going to have points left in. Okay, so let's try making a sketch of this. So we've got a lot of transformations. Like we've got a vertical stretch by 2. We've got a shift up. We've got a shift. This is in the wrong order, but it's a shift left 3. A reflection. And a horizontal compression by a factor of 2. So there's a lot happening. As long as we plot some points, that's all we need to graph it. We do not have to list all the transformations. That's not what they want. So, First of all, does this graph have a start point or is it a center point?
Center.
Center.
Right, it's a center point because it's odd. How do I get the x value?
Set x equals 0.
Set
Or
what
set
equals
the
0?
entire cube root equals 0, right?
Just the radicand.
Yeah, just the radicand.
Set the radicand equal to 0. I'm going to get that. So what do we get for x?
3 over 2.
3 over 2, yep, or 1.5. I'm going to do a decimal because for me when I graph, decimal is easier to graph. So x is 1.5, comma. Now plug it back in to find y, but this should really be not that bad. What's 2 times 1.5?
3,
3. What's 3 minus 3?
0,
Cube root of 0.
0,
0.
0 times 2.
0,
0 plus 1.
1.
1. So basically, whatever's at the end is the y value of your center point.
Yeah, because isn't that the vertical shift?
Yeah, that's the vertical shift. The center point was at 0, and now you shifted it up 1. Okay? So, 1.5 comma 1. As far as like math we have to do for this problem, that's pretty much it. Now we just want to get a couple other points to plot. So let's take this. Let's do 1.51. Should I be plotting points that go in both directions or just one?
Both.
Both. So we're just going to pick some x's between -10 and 10 and plug them in. If you don't have a calculator, you're going to have to plug those numbers in by hand to do it. If you do, you can just type it in and use the, what would I use? The what?
Second table.
Yeah, exactly. Just use the table. So the
Second table.
cube root of 3 minus 2x plus 1. Now, if you want, you can check the point you already have, 1.5 comma 1, just to make sure you did that one right. Yep, we're good. What would be some other good points to check that would fit on my graph?
0.
Yep, 0 is good. We're going to do like maybe 6 or 7 points. What else?
-2.
Yep, -2. Another one?
3.
3? Yep, another one?
4.
That's okay. We got 3. That's pretty close.
8.
Yeah, 8. What else?
12.
That's going to be off my graph. Nothing wrong with it. I just can't fit it.
-6.
-6. All right. All right. I think that's probably enough. If you need more detail, you can do it. Okay. Let's move that up. Make that a little smaller and see what we got. All right. 0, 3.8. 1, 2, 3.8. -2, 4.8. -2, 4.8. 3, -1.8. 1, 2, 3, 1.8. So it gets pretty steep kind of in the middle. What else we got? 8, -3.7. 1, 2, 3.7, I think right there. -6, 6 roughly. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, you might need more points, but I can kind of tell, I see the curve. So it's going to kind of go like this, get pretty steep in there, and then curve like that. Let's see how we did. It might be a little steeper in the middle than I drew it. I think it is, but it's okay. So yeah, it's so steep in the middle that the calculator, remember, when it gets vertical, it's kind of like, wait, how do I do this?
So if you zoomed in, it wouldn't.
Yeah, if you zoomed in enough, it would still look vertical. So yeah, actually it would still have a gap. Yeah. If you zoom out, you could probably hide the gap. Yeah, then it would look smaller. But yeah, there shouldn't be a gap. Okay, so any questions on that? That's basically what we're looking for. Okay. Now, I'm not going to go through all of this one, but if I did, would it have a start point or a center point? Yeah, start point. And to find it, let's just do this real quick. So you would get 4/3, or about 1.3. What would the y value be? -2. Now, a couple people told me you would only plug in numbers going in one direction. Would you plug in numbers bigger than 1.3 or smaller?
Bigger.
Okay, let me pick a number bigger than 1.3. Let me pick 10. What's 3 times 10?
30.
What's 4 minus 30?
-26.
Can we take an even root of a negative number?
No.
No, so we went the wrong way. So we would want to pick numbers that are smaller, like 0. If you plug in 0, you'd be fine. 3 times 0 is 0, 4 minus 0, 0, and you can take the 4th root of 0. So this one is going to curve. Why is it curving to the left? What caused that to happen?
A -3.
Yep. This negative right here. If that was a positive, then you could have picked numbers that were bigger. It would have gone this way. Okay, so any questions on that? All right. So last thing we're going to look at is solving radical equations. Once we go through it, you should be able to solve something like that. This is about as bad as they get. That's like the worst one we're going to do today. So, to solve a radical equation, we have to get one of the radicals by itself. If there's just one radical and it's already by itself like that, fine, that's perfect. But if you have more than one radical, isolate one of them. Doesn't matter which one. Once you isolate a radical, you want to raise each side to the power that would cancel out the radical. So if you have a square root, square. If you have a cube root, cube. Do the opposite of whatever root you have. Now, sometimes you're going to have to do this twice. If your problem has 2 radicals in it, you're going to have to go through it twice. If your problem only has 1 radical, you only have to do it once. But this first one we're going to do has 2, so we're going to have to do it twice. And this is important. Plug your answers back in and check them, because they might not always work. Okay. So what's the first thing I would have to do in example 6? No. What are the directions? What are the steps I said? What do those say to do?
Square both. Isolate them and then square.
Isolate a radical on one side. That's the first step. You've got both radicals on the same side. So isolate one of them. So, which one do we want to get by itself?
You should do plus 4x plus 9 squared because the positives are easier to work with, right?
Yeah, just take this one and move it to the other side.
Yes.
So we're just going to add it to both sides. Yep. So let's start with that. So now we have 6x plus 12 equals 1 plus that.
I guess it's squared.
Yeah, you had said square.
Oh, I'm sorry.
No, it's all right. Now, what do I want to do on both sides? Raise each side to the power. So this is an index of, it's invisible, but what number is there? 2. So square each side. So squared, squared. What do you get on the left?
6x plus 12.
Yep, you get 6x plus 12. So that's pretty straightforward. Now, on the right, how would you do something like this? What do you have to do there?
Square each term.
More than that. How would you, however you would do this out, you have to do that the same way. Right, you have to use distributive property, right? Or some people call it, when there's two of them like that, FOIL, right? So that's how you have to do it. So if it's helpful, you can write this out a second time. 1 plus square root 4x plus 9. And now FOIL. Right. Let's do the first one. 1 times 1? 1. 1 times the square root of 4x plus 9. Another 1 times the square root of 4x plus 9.
2, 4, 9.
2 square roots of 4x plus 9. And the last part, square root of 4x plus 9 times another square root of 4x plus 9.
4 equals 9.
Just 4x plus 9 because it's like square root of 4x plus 9 times itself. So it's like squared. Now, how many square roots are left in this equation now?
2, 1. Well, 1.
Just 1. Yeah. We had 2 originally. By squaring both sides, we got it down to 1. Now, do the same thing again. Isolate that square root, and it's going to be much easier the next time. What could I subtract from both sides to move all my constants over to the left?
4x plus 10, because you could take the 1 added to the
Yeah, so we could do the constants and linear term at the same time if you want. I was just going to do 1, but if you minus 4x from both sides, it gets rid of that. And if you minus 10 from both sides, 10 gets rid of a 1 plus 9. So we got rid of everything at the same time. So what does that give me on the left?
2x plus 2.
Equals 2 square roots 4x plus 9. Now what would we do?
Square both sides.
Not yet.
Not both sides, but 2.
Yeah, divide everything by 2 and you can make all your numbers small. Now what would we do?
Square both sides.
Now you can square both sides. Square, square. X plus 1 squared, what do you get when you FOIL that?
Square plus 2x.
Mm-hmm.
X plus 1.
Plus 1 equals, what's on the right?
4 plus 9.
Yeah, that's the easy part. Now how many square roots are left?
None.
None. Okay, so now we got rid of all the square roots. What kind of equation is this? It's just a quadratic. So what should we get it equal to?
0.
Yep. So if you get it equal to 0, what would you have on the left?
Minus 2x.
Yep.
That's 8.
Yep. And I think that's going to factor.
Oh, wait.
You subtract 4x plus
Oh,
9.
got it.
I was half asleep when I did that.
How is how's that going to factor?
Plus 2 minus 4.
X plus 2.
Yeah, x minus 4.
Check it. X squared minus 4x plus 2x. Yep, minus 2. 2 times negative 4, negative 8. So what would make x 0 here? Or what would make this factor 0?
Negative 2.
What would make this factor 0?
4.
So let's make sure they both work. I'm going to check 4 first.
Oh god.
It's very pretty easy math. What's 6 times 4?
24.
Plus 12?
36.
Square root?
6.
6 minus. I'm just going to put that off to the side. 4 times 4?
16.
Plus 9?
25.
Square root of 25?
5.
Does 6 minus 5 give me what I wanted?
Yeah. That's so perfect.
It's perfect.
It's so
So
satisfying.
crazy.
So this one works. I'm going to circle it. Let's check -2. What's 6 times -2? Plus 12?
Zero.
Square root? 0 minus. What's 4 times, what are we checking? -2. 4 times -2?
1.
Plus 9?
1.
Square root? Is 0 minus 1 1?
No.
No. That one doesn't work.
She's so close.
So -2 is extraneous. The only answer that works here is 4.
That's a lot of math.
Now, I'm not going to do it graphically, but if you were going to do it graphically, all you have to do is put all of that in y1, put that in y2, and then what?
See where they
Interesting.
Just see where they cross. And they are going to cross in one spot. 4. That's it.
Whoa, so why can't we solve everything graphically? Because that'd be so much easier.
A lot of math.
Because sometimes graphing isn't allowed. Yeah.
That's so mean.
Let's check this one. Now, this one, it looks like it could be worse because it's a cube root instead of a square root, but there's only one of them, so I would take this problem over the last one. I think this is easier. What would you have to do on this one?
Multiply both sides by 1/3.
Raise both sides to the third.
Yeah, cube each side. On the left, that's going to give you that. What about on the right? X to the third. So x to the third. What do you think we should do now? If this is going to work out nice. Okay, when we factor it, what do we want to do right before you factor?
I think you should find Kobe for this one.
Colby?
I'm so bad, I have to rewatch this one again.
What do we want to do anytime you want to factor? What do you always do right before you factor? Think of a quadratic.
Quadratic.
Find a common number that you can pull out of it.
It's before you get to that.
That's, never mind, it's not that.
We did it in the last problem.
Quadratic formula.
No, if you're factoring, you're not using quadratic formula.
Roots. I'm trying to find roots.
What did I do before I factored?
Oh, you subtracted the other side. You subtracted
Equal to 0.
Get it equal to 0.
See, come
So-
on, man.
Get this one equal to 0 first. When I factor, I like to have the highest one positive. That's just how you're taught to factor. So let's move everything to the other side. So what will I have?
For the top or the bottom?
Minus
x
squared
plus 2x plus 2.
Jinx. You go over this.
Now, this is factoring a cubic. So it is going to come out nice. What's the only way we can factor something with 4 terms? Special kind of factor.
Try.
Ooh, the
Factor tree.
Oh my god. What's the one? The paired factor.
Yeah, it's like in the pairs.
Yeah. What's
Oh, gotcha.
Yeah, I don't remember what it's called.
Fact.
Group factor, yeah.
That's what.
Dummy head.
Yeah.
What can you factor out of the first 2?
X squared.
And what does that leave you with?
I remember this.
X.
Minus 1.
Now we're hoping to get x minus 1 again, and on a problem like this, I'm gonna make sure that that happens. I'm just checking. I'm sorry, I copied that sign wrong, which would mess up this sign. It was a plus, and I copied it as a minus. So now it's okay. What can you factor out of the second part?
2.
2.
Positive 2. What's left?
X minus 1.
Now, what's common to both of those?
X minus 1.
So now factor that out. What's left in the first term if you take out the x minus 1?
X squared minus, X squared plus 2.
What would make the first factor 0?
1.
And now the second one, what would happen when you set that equal to 0?
Stop.
Oh man.
You can subtract 2.
Okay, I mean you can do that. Now what?
And you get square root if you can't.
You can't.
You get imaginary numbers.
You get imaginary. So there are no answers from here.
So x equals 1.
X equals 1. We're just going to make sure that it works. I think it does. What's 1 squared?
1.
1,
2 times 1?
1.
2, negative 2.
And then plus 2. 1 minus 2. Negative 1 plus 2. Cube root.
1.
1. And we plugged in 1. So 1 equals 1.
1.
Yep, it works. So if you wanted to graph this, you could put what's on the left in y1, what's on the right in y2, see where they cross.
Example 8 times.
Okay, yep, last one. Any question on example 7?
No, I actually understood that.
So, the last one is solve graphically. Can somebody tell me what to do?
What we don't I know what to do.
We don't have to do anything algebraic.
It has a thingy.
You find the intercept.
Okay, so what should I do first?
So on the left side, you're going to plug in the 5th root of 9, subtract x squared.
9 minus x squared, okay,
And the bottom, you're going to write x squared plus 1.
plus 1, okay.
And graph.
Yeah, I'm gonna do zoom 6 just to make sure I have a standard window.
Okay. Oh, that's weird line.
Whoa.
It's
Fancy.
mirrored.
Holy cow. Pretty fancy.
Kill him.
What the?
Whoa.
So there's that little span in between the parabola u. So we're going to do second calc intersect.
Yep, you're looking for this right
Find the
here.
two intersections and the little blue line where it's above the red.
Now, from the last class, I remember what the intersects are. Does anyone need me to show you how to do an intersection?
Isn't it just define
Second calc,
second calc intersect?
intersect. I think it's the 5th option. They intersect at negative 0.73 and positive 0.73.
You remember
So
stuff.
from negative 0.73 to positive 0.73, the 5th root of that's true.
Now, this is an interval, right? From here
Yes.
up to here. Should I include the endpoint or no?
Yes,
Why?
because it's greater than and equal to.
Right there, equal to. And that's your answer. If you pick anything less than negative 0.73, the blue graph is under the red one, way under. If you pick anything bigger than 0.73, the blue graph is way under. They wanted to know where the blue graph was above. So it's just a very, very small section.
Okie dokie. And now the homework.
Any question on that? Excited for the homework?
What?
You excited for the homework?
I'm excited.
Okay.
I'm pumped.
Then I'll give you the homework.
At this and physics.
No, you're ruining the recording right now.
Me oh my.
So the homework is on 255 and kind of skips around. So it's 1, 3, 5, 6, 12 to 14, 20 to 22, 28, 31, 35.
Are you still recording?
Yes. So don't forget, this is the last week of the term. So test this week goes on term 1. If you've got anything else you need to make up, just come see me. Just come see me before the end of the week. I will be after school on Thursday.
Red.